And we're back with the second portion of section 4.5. To summarize the first part, I created this little table for you to review. Basically, when testing for linear dependence or independence, what you want to do is construct your matrix and list the given vectors as columns. Row reduce, you can go to reduced row echelon form as opposed to reduced row echelon form. And any column without a pivot implies the set is dependent. Okay, so if any of the uh, column, the columns in the coefficient matrix has a pivot or lacks a pivot, then the set of vectors is linearly dependent. The columns missing the pivots tells you which vectors in the set are redundant. Okay, so excluding them from your set leaves you with a smaller set that has the exact same span as the larger set. Now, for testing for span, whether or not a certain vector or set of vectors span a certain space, what you want to do is construct your matrix and list the given vectors as columns. Okay, same as step one for independence and dependence. Row reduce. Okay, same as step two. Now look for any row without a pivot. Okay, any row without a pivot implies that the set does not span all of Rn. Okay, so for dependence and independence, you're looking for columns with pivots, and with span, you're looking for rows with pivots. All right, so let's take a look at the next page in our notes. Consider the set of vectors 1, 2, 3, 3, 2, 1, 2, 2, 2, 1, 2, 1. Is this set linearly dependent or independent? If dependent, which vectors can you delete so that the remaining set has the same span as the original set? All right, here we go. So we create our matrix. We're not even going to do the augmented column. Okay, there's no sense in doing the augmented column because you're going to be adding and multiplying and not dividing, but adding, multiplying, subtracting 0. Okay, so that doesn't make sense to look at that. So 1, 2, 3, 3, 2, 1, 2, 2, 2, 1, 2, 1. And again, I'm not going to put the 0 column over here. So this is our coefficient matrix A. Now, we row reduce. So let's see if we can do this rather quickly. Let's leave this 1, 3, 2, 1 there. 2 minus 2 is 0. 6 minus 2 is 4. 4 minus 2 is 2. 2 minus 2 is 2. Okay, so we have that. Multiply this by 3. 3 minus 3 is 0. 9 minus 1 is 8. 6 minus 2 is 4. And 3 minus 1 is 2. Okay, so that's row reduced. Let's scale these. So let's make this 0, 2, 1, 1. Let's make this 0, 4, 2, 1. And this remains 1, 3, 2, 1. Right. So keep going. 1, 3, 2, 1 looks fine. 2 times 2 is 4. 4 minus 4 is 0. So 2 minus 2 is 0. And 2 minus 1 is 1. Okay. Sorry, I didn't want to do that. 1, 3, 2, 1. We're going to leave this 0, 2, 1, 1. All right, we're going to do this one. 2 times 2 is 4. 4 minus 4 is 0. Okay. 2 minus 2 is 0. 2 minus 1 is 1. There we go. All right, one more step. Okay, we're going to take this row and divide by 2. So we have 1, 3, 2, 1 on top, 0, 1, 1 half, and 1 half, 0, 0, 0, 1. Now, that's row echelon form. Pivot, pivot, pivot. Okay. So, what can we conclude about this list? Okay, this list of vectors. Well, first off, there's not a pivot in column 3. So because there's not a pivot in column 3, that means that this vector right here, 2, 2, 2, is a combination of the other 3. Okay, so in other words, the span of 1, 2, 3, 3, 2, 1, and 1, 2, 1 is equal to the span of the complete list. 1, 2, 3, 3, 2, 1, 2, 2, 2, and 1, 2, 1. So this is an abbreviated list that has the same exact span as the previous list. Okay. Second, so this list, sorry, I won't get to that point yet. Now, note that there's a pivot in every row. Okay, because there's a pivot in every row, we can say that the span of this list spans all of R3. So that means, and when I say this list, am I talking about the one with 3 or the one with 4? And the answer is both. It doesn't matter, because the span of each of these lists are exactly the same. And what is that span? All of R3. Why is it all of R3? Because there's a pivot in every row of our matrix, our row echelon form version of our matrix. All right. Now, is this list of vectors linearly independent or linearly dependent? And the answer is it's linearly dependent. It's dependent because this vector 3 is a linear combination of the other 3. Okay, had I deleted this vector 3, okay, and looked at the list of vectors 1, 2, 3, 2, 2, 1, and 1, 2, 1, this set of vectors would be linearly independent, because you would have, and again, you're just kind of deleting column 3 from your field of vision. Now you're going to have a pivot in every column. All right. So let's answer some of these quick response questions. Okay, look at the list of vectors 2, 4, 1, 3, and 3, 5. Can you determine, without doing any row operation, sorry, my dog is barking, whether or not the list is linearly independent or linearly dependent? Let's take a look. Okay, so let's make this a matrix. Okay, the columns are 2, 4, 1, 3, and 3, 5. Okay, and we're going to look to see if there's a pivot in every column. Okay, now what's the most number of pivots that we can have? Where each row can only have one pivot. Each column can only have one pivot. I have 2 rows, so therefore I can have at most 2 pivots. Okay, if I can only have 2 pivots, then there can't be a pivot in every column. So therefore, I know without doing any work that this set is linearly dependent, because the most number of pivots I can have for a 2 by 3 matrix is 2. Okay, the most number of pivots I can have for a 3 by 2 matrix is 2. Okay, and therefore not every column can have a pivot, and if not every column can have a pivot, then one of these vectors is redundant, therefore linearly dependent. All right, what about this? Okay, linearly independent or linearly dependent? Well, the thing to notice here is one of the vectors is the 0 vector, and the 0 vector can always be obtained by taking 0 times the non-zero vector. So therefore, this vector is a scalar multiple of this vector and thus linearly dependent. What about 3? Okay. Well, this would generate a 3 by 2 matrix. It would look like 2, -6, and 4, -1, 3, and -2. Okay, so I have a 3 by 2 matrix. I can have at most 2 pivots. Well, 2 pivots is good because I only have 2 columns. So I can have a pivot in every column. Okay, but notice that there is a relationship between these 2 column vectors. Okay, column 2 is -1/2 of column 1. And since there's a linear dependence between those 2 vectors, this is also linearly dependent. Okay, so just by looking at that, we can see whether or not the set of vectors is independent or dependent just by examination. Lastly, find an example of any 3 vectors in R3 that are linearly independent. If possible, and if not possible, then state why it's not possible. So, you want 3 vectors in R3 that are linearly independent. How about that? Okay, there are vectors in R3. When you look at the corresponding matrix, there's a pivot in every column. Therefore, this set of vectors are linearly independent. Find an example of any 4 vectors in R3 that are linearly independent. Well, here's where we run into trouble. Okay, if we add a 4th column, okay, you can only have a pivot in 3 of those columns. That means the 4th column that you add, there's not going to be a pivot, and therefore the list will be linearly dependent. So that one's not possible. Find an example of any 3 vectors in R3 that span R3. Okay, well, how about the first? Okay, there's a pivot in row 1, there's a pivot in row 2, there's a pivot in row 3. So not only are these 3 vectors independent, they're linearly independent, they also span all of R3. And that should make sense, because I could take x times the vector 1, 0, 0, plus y times the vector 0, 1, 0, and z times the vector 0, 0, 1, and obtain any old vector x, y, z that you want. All right, find a vector, an example of any 3 vectors in R2 that do not, that's R3. Find an example of any 3 vectors in R3 that do not span R3. So we want 3 vectors in R3 that do not span R3. So how about I do that? 1, 0, 0, 0, 1, 0, 1, 1, 0. Okay, where 1, 1, 0 is a combination of vectors 1 and 2, just 1 and 2 added together. Now, there's a pivot here and a pivot here, but not a pivot there. And so because there's not a pivot in the third row, it's not going to span all of R3. Find an example of any 4 vectors in R3 that span R3. Okay. Let's just take the original spanning set and add any vector that we want. 1, 1, 1. Okay, so we know that these 3 vectors already span all of R3. Add on a 4th. It doesn't change the span. Find an example of any 2 vectors in R3 that span R3. So now we're looking for 2 vectors in R3 that span all of R3. Remember, this is going to correspond to a matrix that would be 3 rows by 2 columns. Okay, so I can have a pivot here and I can have a pivot here, but I can't have a pivot down here. I can have a 1 here and a 1 here, make these zeros. But I can't have any pivots down here because the most number of pivots I can have in a 3 by 2 is 2 pivots. So that means there's going to be 1 row that doesn't have a pivot. And if there's 1 row that doesn't have a pivot, I can't span all of R3. So this one is not possible. Okay, so that was the last bit of section 4.5. Up to come is section 4.6, which ties together the idea of linear independence and span a little bit more than this video does. Take care and have a great one.